All right, we're back and we're on a roll. We are in the process of classifying an image from Yellowstone National Park taken after the wildfires of 1988. And the last two videos we learned how to define the training polygons, look at whether our classes are spectrally separable, and then in the previous video we just looked at kind of doing a poor man's decision tree using conditional statements in ArcMap. Now that decision tree we just looked at, that's an interesting technique. It's very intuitive and kind of gives you, I find it helpful to think about what you're doing. But what we're going to do now is move into some of the more sophisticated classification options in ArcMap. And of course ArcMap is not the most powerful software for image classification. Envy is much more powerful and other choices as well. But if ArcMap's all you've got, it works pretty well and has a few key options that could be really helpful. And so the options we're going to look at here are a little more complicated than what we looked at with decision tree. And we're only going to take two examples. We're going to look at a supervised classification example using the maximum likelihood approach, and then we'll look at an unsupervised classification approach using the ISO data. And I'll first give you a little overview of these techniques, then we'll look at how to apply them in Arc. So the supervised classification example is the Gaussian maximum likelihood approach. And the way this works is visualized here. Let's say we had 6 desired user classes. That'd be water, farm, hay, corn, sand, and urban. So all these different classes, and in this case we've plotted up each pixel, each training pixel in band 3 versus band 4 space, and we can see that they're nicely separated from each other, so that's promising, albeit possibly fictional. And the way that the maximum likelihood works is that the algorithm creates a probability density distribution, not just in 2-dimensional space, but actually in n-dimensional space, where n is the number of bands that you have. And the more training pixels fall in a given part of that dimensional space, the higher the probability value is that an unknown pixel, if it fell there, would also be a part of that class. So then what we do is we define this probability field. So for urban, the highest probability of being urban would be right in here. For water, it'd be right in here. For hay, the highest probability of being a hay pixel would be right in here. So you can think of it also kind of as a bullseye, where if the unknown pixel comes up near the center of the bullseye, that means it has the highest probability of being associated with that training class. Another way to view this is actually as a 2D probability density plot, where the peak of the plot, if you take an unknown pixel and it falls near the peak of one of these plots, then it gets assigned a very high probability of being, say, forest. And if it falls off near the edge, it has a very low probability. And of course, things that are spectrally simple, like sand, will have very narrow probability distributions. Things that are spectrally complex, like urban settings or urban pixels, will have very wide probability distributions. One advantage of this technique is that if a pixel falls in the middle, away from all of these things, it's very easy to not classify it. You can simply say, look, if this pixel doesn't have a probability greater than, say, 5% of being in any of these groups, then don't classify it at all. And that's a simple way to exclude pixels that really aren't represented in the training data and probably shouldn't be classified. So in terms of an unsupervised example, I'll start out with the k-means classification algorithm, and then I'll show you the ISO data. Now keep in mind, unsupervised classification means that the user has not provided any training information at all. The user has not suggested a set of classes that they would like to emerge from the classification. Instead, we're letting the computer go ahead and identify the arbitrary classes that are most spectrally unique. So sometimes we'll call those spectral classes. Now, in some of these algorithms, the user can specify the number of classes. So you could say, I want the 6 most spectrally distinguishable classes. And in the k-means algorithm, what the computer does is it picks some seed points. So those would be red, green, and blue here. And by the way, we're looking at data plotted in band space. So each point is a pixel, and the x-axis would be like band 1, the y-axis would be like band 2. So we start out with these means, and then we have a bunch of unknown pixels that we're trying to classify. And the computer simply, in the simplest version, assigns an unknown pixel to the class that it's closest to. So it uses the Euclidean distance in n-dimensional space and assigns it to whatever class it's closest to. So in that result, anything that was up here would have been in the red class, anything here in the green class, here in the blue class, because those pixels were closest to those means. But that's just the first iteration. The algorithm then goes on to repeat the iterations, and it randomly defines a new set of means. So it perturbs the system a little bit and says, well, that was okay, why don't we try this set of slightly different means? And it will compute that new mean by taking the mean of all the classes that were actually in that original grouping. So it's going to take the mean of all these green squares. That's going to shift it from here down to here. So it's got a new mean. Then it's going to run the classification algorithm again. And this time, this pixel is now going to be in the red group, whereas there's no change between the blue and the green. And it will repeat that redefinition of the mean and reclassification until there's no change. And then the groups have been optimized for their spectral differences. Now, the isodata approach is very similar, except the clumping and splitting of the groups is based on the spread in the data rather than the distance from a pixel to a given mean. So start with some number of classes, and then after each cycle you would assess the means, and if the means are too close together, then those two classes might be merged and a new class might be defined somewhere else. But likewise, if a class has too large of a standard deviation, if the points within that class are spread too high, that class would then be split into two separate classes and the iteration repeated. So in both of these algorithms, there's an iterative process in which you're either trying to minimize the total distance between pixels and their group means, or you're trying to minimize basically the spread of data or spread of pixel values within all of the different groups. So we've got our project open in ArcMap. Here's the Landsat image of Yellowstone. Recall in the previous video we defined 4 user classes. We had water, we have meadow, we have forest, and then we have burned area. Let's try maximum likelihood first, and that's going to be up under the classification toolbar. That's where they all are. And we can choose maximum likelihood classification. But before we do this, we need to actually save out a signature file. So let's go back. We'll go into our training polygons, our training manager, and then we'll go over here and click create a signature file. And I'll call it Yellowstone signature. And that's going to save the relevant spectral information so that you can bring it in anytime. Back to maximum likelihood. Okay, so I just got everything ready here to save us a little time. I've got the signature file input here. I've given my output raster a name and a .tiff extension. That's important. I'm saving it in my folder. The other thing we want to set here is the rejection fraction. So this is the probability between 0 and 1 that the pixel actually can be assigned to a given class. And I'm going to go ahead and say if there is less than a 5% chance, or 0.05, that the pixel belongs to any given class, then go ahead and reject that. Don't classify it. In fact, maybe I'll make it 10%. Then this is the weighting. And this is asking, should you weight the classes based on anything? For example, you could put in a file that has predefined weights, or you could weight them based on the number of pixels in the training polygon. But in this case, we're just going to give them all equal weight. And also, I'm going to go ahead and specify a confidence raster. And this is going to be really useful to see which pixels were well classified and which weren't. So hold on, I'm going to set that up. OK, so I've called that max likely confidence, also with a .tiff extension. And of course, we're inputting our Landsat. I think we're ready to go. I'm going to wait a second. OK, so here's the result of that supervised maximum likelihood classification. You can see pixels numbered 1 are water. I've colored those in blue. Pixels numbered 3 are meadow. Those are in light green. Pixels numbered 5 are forest. Those are in dark green. And black is burned areas. So one big difference between this and the decision tree, you can quickly see that it looks roughly the same, but in this case many pixels were not classified. That's because we gave it that 10% threshold. And in particular, we can see a lot of pixels kind of around the periphery weren't classified. Those are in areas where maybe we didn't give a good training polygon. So for example, if you look down some of these kind of mountainous ridge lines down here, I don't know if that's snow. I guess it's rock, actually, bare rock and snow up in some of the Wind River Mountains or the Absaroka Mountains. We didn't put in a class for bare rock or snow in the high mountains. So you can see that a lot of those mountain ridges went unclassified, and that makes sense. Now it also put out this maximum likelihood confidence raster. And so this shows a measure of how confident the classification was for each pixel. And the scale here is that red is high numbers, that's very unconfident, and green is low numbers, that's very confident in the class assignment. So obviously our highest confidence was water. Some of these areas within the training polygon for water were very, very confident. And then we can see other areas that were very unconfident are in bright red. For example, these ridge lines over here that we never gave it information about were classified with a very low confidence level. Okay, so now let's close out those and let's try the ISO data. And so again, here are our training polygons, but keep in mind we won't be using those. ISO data is an unsupervised technique, and so these training polygons are irrelevant now. We're not going to give this any spectral information. But again, we'll go back to the classification tab, go to ISO cluster, and I'm going to go ahead and fill this in and then get back to you here. Okay, so I've specified the number of classes to be 8, so it's going to come up with the 8 best classes. I've given an output file name with a .tiff extension. The minimum class size is the minimum number of pixels that should be in a given class. I've gone ahead and made that to 1,000, recognizing that I don't want any tiny classes. In general, this number should be at least 10 times bigger than the number of bands that you have. And the sample interval is basically, it's only going to consider each pixel within an n by n block. So if you do 10, it will consider 1 pixel out of every 10 by 10 block. And actually reduce that a little bit to 5 to get a little higher resolution classification. I'm not going to output a signature file. And of course, we're doing this on the original Landsat band. All right, let's see how this goes. Okay, so it spit out the result, and the things look pretty promising. We've got our 8 classes here in the ISO cluster raster that was just produced. One thing that jumps out right away is obviously water. Did successfully get its own spectral class. That's class number 1, shown in gray. So we can really clearly see the bodies of water. So that's a case where one of the spectral classes output by unsupervised classification happily was the same as one of the user classes that we had wanted in our supervised classification. So that's great. But how do we do in other categories? Well, in terms of meadow, it looks like maybe class number 5 corresponds to meadow, these kind of yellowish blobs. And I'm just going to take a quick look and kind of go back and forth. You can see bright green is meadow in this image, and that correlates reasonably well with the kind of dark yellow right in those two areas. So it looks like meadow maybe did okay as well. And then, of course, burned is up here in class 7. Looks to be this teal color. Looks like it is burned areas and did a pretty nice complete job of that. So in general, it looks like we did pretty well here. And that's because a lot of the classes we were trying to get were, in fact, pretty spectrally unique. So that'll wrap it up for this video. Join us for our next video, where we'll add a UTM grid, but actually the video after that, number 30A, I'll show you how to do a little bit of post-classification smoothing so that we can potentially reduce the number of classes and clump pixels together if we want to. See you shortly.